In computational mathematics, an iterative method is a mathematical procedure that generates a sequence of improving approximate solutions for a class of problems. A specific implementation of an iterative method, including the termination criteria, is an algorithm of the iterative method. An iterative method is called convergent if the corresponding sequence converges for given initial approximations. A mathematically rigorous convergence analysis of an iterative method is usually performed. However, heuristic-based iterative methods are also common. In the problems of finding the root of an equation, an iterative method uses an initial guess to generate successive approximations to a solution. In contrast, direct methods attempt to solve the problem by a finite sequence of operations. In the absence of rounding errors, direct methods would deliver an exact solution. Iterative methods are often the only choice for nonlinear equations. However, iterative methods are often useful even for linear problems involving a large number of variables, where direct methods would be prohibitively expensive even with the best available computing power. Attractive fixed points. If an equation can be put into the form f equals x, and a solution x is an attractive fixed point of the function f, then one may begin with a point x1 in the basin of attraction of x, and let xn plus 1 equals f for n1, and the sequence xn, n1 will converge to the solution x. Here xn is the nth approximation or iteration of x, and xn plus 1 is the next or n plus 1 iteration of x. Alternately, superscripts in parentheses are often used in numerical methods, so as not to interfere with subscripts with other meanings. Equals f, if the function f is continuously differentiable. A sufficient condition for convergence is that the spectral radius of the derivative is strictly bounded by 1 in a neighborhood of the fixed point. If this condition holds at the fixed point, then a sufficiently small neighborhood must exist. Linear systems. In the case of a system of linear equations, the two main classes of iterative methods are the stationary iterative methods and the more general Creel subspace methods. Stationary iterative methods. Stationary iterative methods solve a linear system with an operator approximating the original one, and based on the measurement of the error in the result, form a correction equation, for which this process is repeated. While these methods are simple to derive, implement, and analyze, convergence is only guaranteed for a limited class of matrices. Examples of stationary iterative methods are the Jacobi method, Gauss-Seidel method, and the successive over-relaxation method. Linear stationary iterative methods are also called relaxation methods. Creel subspace methods. Creel subspace methods work by forming a basis of the sequence of successive matrix powers times the initial residual. The approximations to the solution are then formed by minimizing the residual over the subspace formed. The prototypical method in this class is the conjugate gradient method. Other methods are the generalized minimal residual method and the biconjugate gradient method. Convergence of Creel subspace methods. Since these methods form a basis, it is evident that the method converges in n iterations, where n is the system size. However, in the presence of rounding errors this statement does not hold. Moreover, in practice n can be very large, and the iterative process reaches sufficient accuracy already far earlier. The analysis of these methods is hard, depending on a complicated function of the spectrum of the operator. Preconditioners. The approximating operator that appears in stationary iterative methods can also be incorporated in Creel subspace methods such as GMRES, where they become transformations of the original operator to a presumably better conditioned one. The construction of preconditioners is a large research area. History. Probably the first iterative method for solving a linear system appeared in a letter of Gauss to a student of his. He proposed solving a 4x4 system of equations by repeatedly solving the component in which the residual was the largest. The theory of stationary iterative methods was solidly established with the work of D.M. Young starting in the 1950s. The conjugate gradient method was also invented in the 1950s, with independent developments by Cornelius Lanczos, Magnus Hestenes and Eduard Stiefel. But its nature and applicability were misunderstood at the time. Only in the 1970s was it realized that conjugacy-based methods work very well for partial differential equations, especially the elliptic type.